Bismillahirrahmanirrahim. Today we're going to start beam design, singly reinforced beam design. But before we go design, I will concentrate on some fundamental requirements for the design. So you get just don't go further like you do in your previous lecture 4. You just solve the example, and many of you even didn't touch the basics. Many of you even, as I guess, many of you even didn't touch the basics. So make sure first study the basics, then go for example.
What do you mean by basics, sir?
In your lecture 4, if you see, there are some previous slides. Many of you didn't do that. They directly go and solve the slide, last 4 slides for the examples. So don't do that. Just try to read out first, understand the previous slides. Okay, here something that some of teachers explain in the very early stage, but I think I am doing right now. It would not be very negative point. So it is some load combinations and load cases. There are 6 different. Now we are going to deal with the design, so we have to understand what kind of loading is acting on the beam or other things. Let's say we are sitting in this classroom. There are different types of loadings. The load of this table or something this are hanging on the slab is dead load. Is dead load. If this is here, it can move. It will not be considered as dead load.
It's type.
Alright. This one is fixed. This is dead load. Something hanging with the walls, with the doors, is dead load. If a person is dead, and he is on some kind of slab or beam, it would not be a dead load. It would decompose with the time. Good point. If someone put a book over here and it keep on here, you don't have time, you don't know it would when someone pick it up. Until the time it would be here, it would be dead. Clear? By the time it would be in this place, it would be dead load. If one person daily just take out 5 pages every day, it would be live load. Every day is this reduction that I can. So I cannot give you every single example of dead load and live load. Let's say in my paper question, I give you something, some donkey is died on the road or something surrounding. So you have to understand, either it comes from dead load, live load, whatever. I cannot, there are so many examples. So during my paper, maybe I can have some other thing to consider as a load. So you need to understand the basic concept, what is the dead load and live load. Similarly, the things are wind loads. You know there are just, they put on something on the roof. There is there's very high wind velocity there. Similarly, wind puts some pressure on these walls and on all these sections. There's something complex about the wind, but I didn't add over here because they are normally considered more preferable in steel structures or the roofs, the slopy roofs like this. So similarly, here in this diagram, you can just find some dead loads on the roof. Is it clear diagram? Not clear. Not very clear, but the result is not very clear. I just read out for you here. This is dead load here of the roof. Alright. Now here is the collected snow. There is snow on the roof, sir. On this side here. Here. This is collected snow on the roof. That is considered as the yes, that is considered as the live load. This is the snow on the roof. So because the snow will get reduced with the time, or the rainwater would reduce the time, remove the time, that would be considered as the live load. Life. So load of the walls itself is the dead load. Where the load of the roofs or slab is considered as dead load. Load of the beam itself is considered as the dead load. So there are some combinations. Here is an example of the live loads collected water also. Let's say in the beginning I give you an example of overhead tank.
Yes.
So that water will be considered as a live load, not as a dead load. Similarly, here is the soil and hydraulic pressure in the foundation. Soil and hydraulic pressure in the load, these are the considered as the dead load also. If there is conditional, if you if you say that soil pressure is actually hydrostatic pressure, you know what is hydrostatic pressure?
Yes.
Normally, shape of hydrostatic pressure is like this one. Let's say this is the level of your water, and this is your wall. Water is standing there. The hydrostatic pressure increases with depth. This pressure will determine depth, specific data of water increase total depth, how much it is. So that is hydrostatic pressure. Similarly, soil have the pressure. So the foundation, if this is the soil side, soil puts some pressure on it. So if we consider its water on the side, hydrostatic pressure of water, and the same way, if the water is reducing, water is removing from it, so water level reduces. So ultimately, hydrostatic pressure reduces.
Sir, this pressure is not for our head transfer, for head pressure formula.
That's the same thing.
Both are same.
It's hydrostatic pressure. The formula is the same. This specific pressure is called hydrostatic pressure. The standing water puts the pressure. And there is the different combinations. Load factor is the factor by which a load is to be increased. If you remember, in our previous lecture, where I discussed the design philosophy, different design methods, I mentioned the difference between strength method and other working stress method and all these things. I clearly mentioned that in strength design method, we do apply load factors on loading conditions rather than the materials. But in the working stress method, with safety factors, the factor of safety, we put on the material side, but in this method, we put on the loading side. Here you see 1.2 is the factor. So this is the load combinations. You have to use the available load combination. So load combinations here are different load combination, and you might have some other load combination also in accordance with the wind conditions, with the earthquakes and all these things. Because there are further load conditions, but we would restrict ourselves to these conditions. Yes, अगर वो रिमूव हो रहा हो तो आपके सर ओवरहेड वाला वो लाइव लोड
वो भी तो रिड्यूस होता जाता है सर if the position is fixed with magnitude by time passes this is called dead load.
If position is fixed with magnitude of the load, that is fixed dead load. कहाँ से आ गया सीधा फसला वो तो हर मगर डेमल होता है
दोनों सर वो तो
Third class.
फर्स्ट क्लास सर
okay anyhow so this is a load coefficient combination clear. So in strength design method, I repeat again here, applies the bigger part of factor of safety on loads and smaller part on the material strength. In working strength method, they put the bigger part on the factor on the the material strength. I discussed this in details, and if you, I think I have the video also of this part where we do the video I have on my own YouTube. Part 2 is not on my YouTube, but part 1 video is on YouTube. You can just check in details about all these methods and factor of safety applications because it is after so many days. So I don't think so you are fresh-minded about this factor of safety and all these things. So in this method, strength design method, we put a bigger part of factor of safety to the loading conditions and a smaller part, bit smaller to the material side. Here is the simple the stress strain curve of the concrete. The same thing is the maximum strain that we use is 0.003. Further, we will check some strain relations also. That is on the failure types of different failure behaviors. So they will check some strain 0.005 also, 0.004 also, but take 0.003 as a maximum for the crushing strength. If the crushing strength reaches or the crushing point reaches, to that point the strain is 0.003. One is the average stress, average strength of concrete. The average strength is normally the area under the curve divided by 0.003. This is termed as the the average strength. if FC prime, if concrete compressive strength is less than 30 megapascal, in that case, if FC prime the 28 days compressive strength of concrete is less than 30 megapascal, in that case the average compressive strength will be 0.72 times of FC prime. See, here is the one factor is included here, beta 1. The beta 1 factor is average strength divided by crushing strength. The average strength of the concrete and divided by the total crushing strength to which it concrete get crushed. That is beta 1 factor. And normally in this case, if you see less than 30, if the concrete compressive strength is less than 30 megapascal, in that case the average strength is 0.72 FC prime and the concrete crushing strength is 0.85 FC prime. So in that case, beta 1 would be equal to 0.85. Average strength is the area under this curve divided by 003 is the strain. The total curve stress strain curve is clear to you. The stress strain curve, the area of the stress strain curve divided by the strain for the region. Strain for the region is mentioned over here, 0.003. So the ratio of these gives you the average strength. Beta 1 is the ratio of average strength to the crushing strength. Beta 1 is the ratio of average strength to the crushing strength. In case of FC prime or 28 days compressive strength is less than 35 megapascal. In that case, the beta 1 value is 0.85. Okay? सही है, मैं भी गलत समझता फिर मैंने कैलकुलेट किया था, ठीक आता है 0.847 आता है, कैलकुलेट कर लो भी. Okay, there is one thing a bit similar to like equivalent concrete area in cracked and uncracked section. It's similar here, Whitney stress law. Whitney stress law. Don't read it, Brittany. क्या बोलने लगा था? Whitney stress diagram, Whitney stress block is it. Actually, this is equivalent stress diagram that is made in such a way that it has the same area of that actual stress diagram. And this stress diagram develops that the concrete, the lower part of the tension part of the beam is the crack, and the upper limit and the upper part of the concrete and the above compression part of the concrete is also in crushing. Just has reached the crushing strength. So that is 0.85 FC. No, that has not been crushed, I think. That passes that beyond the elastic range. That is no more in the elastic region. The compression part is no more in elastic region, and the lower part or the tension part has cracked already. So in that case, it comes to be 0.85 FC prime and this parabolic. But we are converting into, for parabolic, the problem is we cannot find out duplicate the centroidal the center of the action of the point of action for the compression force. Average compression force, we are resultant compression force. So to accommodate that and to facilitate, we convert or we replace this parabolic form to with equivalent rectangular area. Clear? To identify, to locate the point of application of the resultant compression force. So in the same case, here is 0.85 FC prime. We take my average strength. The average strength, we are trying to relate both of these. Average strength into B and C. You see the C is the depth of this area. Here is the C of this area depth. So B is its width. Alright, so F average into BC is this one for this actual stress diagram for the Whitney stress. This comes to be A. This is equivalent here. We take it equal to A. Alright, we take it is equal to A. 0.85 FC prime would be the same as 1. So here this is the FC prime and this is the area of that one. So it is 0.85 FC prime here. So here we find the value of A. What would be the value? Actually, this diagram don't get confused. That we first get the diagram. We get the diagram, later on first we make a relationship. we assume that this is for sure, we know the depth of C. We don't know this value, how much it is. But we assume it is some value of A. It is some value A. Then we equate both to get this value A, what actually is. So we get a relationship like this in case of if Fc prime 28 a compressive strength is less than 30 megapascal. If you remember, this beta value is for the case if Fc prime is less than 30 megapascal. If some any other case, then you can just take this value A is equal to beta 1 times of C. Okay. So beta 1 is 0.85 for Fc prime less than 30 megapascal here. लेकिन सांस कैसा आ रहा है? यार आपको बताना किया है इसलिए कि जो मैं बताया था हम इसको कन्वर्ट इसलिए करें. हाँ यार कुछ लोग देखा तो इंग्लिश में भी सब कर जस्ट रेज हैंड के उर्दू में रिपीट कर देगा नो प्रॉब्लम. अब हम इसको जगह हमारे पास ये पैराबोलिक शेप है वहाँ पे हमें थोड़ी प्रॉब्लम होती है रिजल्टेंट फोर्स की लोकेशंस के लिए. अब उसको अकोमोडेट करेंगे हम इजी टू गेट टू फैसिलिटेट अस दे यूज द मीट्रिक स्ट्रेस ब्लॉक कवलेंट स्ट्रेस जो है उसको एक रेक्टेंगुलर शेप में कन्वर्ट कर देते हैं. सो वी कैन जस्ट फाइंड दैट हाफ ऑफ दिस डेप्थ वुड बी द लोकेशन ऑफ द कंप्रेशन फोर्स. दिस शेप कन्वर्ट. So value of beta 1 decreases, make a note of this thing, that value of beta 1 decreases by 0.05 for every 7 megapascal increase in strength. Value of beta 1 decreases by 0.05 for every 7 megapascal increase in strength. If 37 megapascal is the strength, what would be the value of beta? 37 megapascal. If it's the 28 days compressive strength, then what would be the value of beta 1? Sorry, 0.80. Got the point? How much is multiply by 0.5 नहीं minus 0.05 करना है. 0.85 उसकी वैल्यू है उस केस में जब ये 30 मेगापास्कल हो. अब नीचे स्टेटमेंट ये कह रही है कि विद इंक्रीज ऑफ एवरी 7 मेगापास्कल द वैल्यू ऑफ बीटा रिड्यूसेस 0.05. आप वहाँ से 7 मेगापास्कल इंक्रीज करते जाएं और दूसरी वैल्यू जो उसकी रिड्यूस की जाएगी. बट द मिनिमम मस्ट बी 0.65. यू कैन नॉट गो बिलो 0.65. Here is the location of neutral axis. You know this situation diagram very well. Here we just transform the actual stress diagram to the witness stress block. You see here, we transform the actual stress diagram to the witness stress diagram, and in this case, the value of T is equal to area of shear into F. This is a simple relation. Do I need to explain this relation? T is equal to what, why, and how? So here we just replace Fs is equal to Fy. Just because if you see this strain diagram here, in this case, both yield stress and Fs both are at the same location. See here, this part. Here, in this case, value of Fs or the stress developed in the steel is the same as of its yield stress. The value of stress developed in the steel is same as a yield stress. So that's why we replace this value of the stress developed in steel equal to the yield stress. All right. Further, the value of CC here, this one C would be 0.85 times Fc prime into this area. B A into area. B is the its width, the section width of course, and A is this depth of the witness stress block. A is the depth of witness stress block. Now this lever arm, the moment arm, whatever you call it, it is D minus A by 2. You know how it is D minus A by 2? Yes. The distance from here, here to here is the D, and A minus 2 is the from the top. So D minus A by B. Clear? Further, for equilibrium condition, we say both stresses are equal here. From here, you can find the value of A again. And of course, C would be equal to alpha A over beta 1. The same relation A is equal to beta 1 C. Equation just rephrased. Just keep this slide in mind, because next we have to use this slide again. Just keep it in mind, this diagram, what we do here. So something is resisting moment capacity. The resisting moment simply the tension force into moment arm and the compression force into moment arm. See this one? T and C is, T is the tension force and C is the compression force. So the for steel strength is T into LA, the moment arm and tension stress, and for the concrete strength, that is is equal to compression force and the moment arm. Balanced steel ratio. Steel ratio is the area of the ratio of total area of tension steel to the effective area of the section. If you remember the problem you solved, there you take rho is equal to AS over BD. BD. D is the effective depth.
Yes.
D is the effective depth of section. The same thing is here. Area of steel, tension steel to the effective area of the section. Rho B corresponds to the amount of steel which will cause yielding of steel at the same time when concrete crushes at ultimate state. Important to note this thing. Balanced steel ratio. You need to know very well the balanced steel ratio. Rho B corresponds to the amount of steel. This is how much steel we are using. We are using that much amount of steel that would start yielding when concrete will get crushed. कि ये उतनी अमाउंट हम स्टील की यूज करेंगे कि जब कंक्रीट क्रश हो उसी वक्त ये भी यील्डिंग स्टार्ट करे. स्टेटमेंट मींस बैलेंस स्टील रेशियो है वो रेशियो स्टील की इतनी अमाउंट है कि जब वो अगर हम एंटर करेंगे तो जिस वैल्यू पे आके, जिस लोडिंग कंडीशन पे आके, जिस स्ट्रेसेस के ऊपर आके, जिस कंडीशन में आके कंक्रीट क्रश होना शुरू होगी वहीं पे वो भी यील्ड करेगा.
सर मतलब स्टील
जी जी
जिस टाइम सर कंप्लीट क्रश हो जाएगा स्टील में भी उसी टाइम सर
वो यील्डिंग शुरू हो जाएगी. जी जी यील्डिंग प्रोसेस वही कह सकते हैं आप. अब रेफर टू द स्लाइड दैट आई जस्ट आस्क्ड यू लोकेशन ऑफ द न्यूट्रल एक्सिस. वहीं पे हमने यही रिलेशन दिया था, रिमेंबर. अब फॉर बैलेंस स्टील रेशियो, अब बैलेंस स्टील रेशियो में हमारे पास जो है, अगर हम इसको एरिया ऑफ स्टील को रिप्लेस करें बैलेंस स्टील रेशियो के बाद के लिए, समझ आइए इस चीज़ की. अब यहाँ पे एरिया ऑफ स्टील ओवर बी डी जो है, अब यहाँ पे हमने रो बी को क्या नाम है, एरिया ऑफ स्टील को एरिया ऑफ स्टील किसके बराबर हो जाएगा, रो बी इंटू बी डी. दैट माय पॉइंट.
यस सर.
या फिर फिर कोई ये ना कि सर वाइट बोर्ड यूज़ करें. अब ये रिलेशन है हमारे पास, इसका तो पता है. अब यहाँ से हमने क्या किया, एरिया ऑफ स्टील की वैल्यू फाइंड की और उसको यहाँ पे पुट कर दिया. ठीक है. अब ये एरिया ऑफ स्टील की वैल्यू यहाँ पे पुट कर दी, बाकी सारा वैसे का वैसा आ गया. अब ये 20 सबस्क्रिप्ट आया ये शो करने के लिए कि जब हम बैलेंस स्टील रेशियो शो कर रहे हैं उसको जो विटनेस स्ट्रेस ब्लॉक की जाए उसको शो करने के लिए आपने मेथड दिया सबस्क्रिप्ट. अब यहाँ से आप रो बी की वैल्यू फाइंड कर सकते हैं गिवन सिस्टम के लिए. कि अगर उसकी FC प्राइम आपको नोट हो, आपका वो नोट हो क्या नाम है, ये स्ट्रेस आपको नोट हो, अगर आपको सेक्शंस की डेप्थ भी नोट हो और उसका विटनेस स्ट्रेस डेप्थ भी नोट हो, तो आप ये फाइंड कर सकते हैं कि इस सेक्शन के लिए हम कितनी स्टील फाइंड करेंगे. टू फाइंड द स्टील फॉर सेक्शन इज द डिजाइन. फाइंड द स्टील. सॉरी
सर क्या
नहीं आप बताओ
सर. B into D, D is effective depth. B is the section of B, section of all
A B
no B only
where is B?
AS divided by BD. D is the effective depth and B is the width of
B is the width of the section. Width of the section.
steel section.
Steel section, no. Concrete section. The word section I mean everywhere is the concrete section, beam section. Alright? So let's say here is we have stress diagram. We take this one, that ultimate strain developed in concrete is 0.003, and here the strain is equal to epsilon s and epsilon y, and this one is the depth of actual stress diagram C at the balanced steel ratio. You remind that diagram that there was C was the depth of actual stress diagram. Got my point?
Yes, sir.
C was the depth of actual stress diagram. We write the subscript because of for the balanced steel ratio condition. And on the other hand, the lower part is D minus CB. The total depth of the effective section is the D, and the remaining part below the neutral axis, that comes to be D minus CB. Clear this point? So we have two triangles here. One triangle is this one ABC, and the other triangle is this one. Sorry, the other triangle is this one. Okay, ABC and ADE. So you know the comparison of triangles. You know this concept.
Yes. Yes, sir.
Let me take CB. CB. Where is CB? This is CB. This CB over 0.003 would be equal to D minus CB over epsilon y.
Yes. Size ratio, sir.
Sides ratio. CB over this one is equal to D minus CB over this one. Clear?
Yes, sir.
यहाँ से आप CB की value find करें, that would comes to be this one. Clear? Mathematical है?
Yes.
Problem होने को?
No.
यहाँ से आप further CB की value find करें. अब epsilon y is equal to yield stress over epsilon ES, modulus of elastic stress. Clear है?
Sir, please explain this point.
आपने पहले रिलेशन पढ़ा था, एक तो मॉडुलस ऑफ इलास्टिसिटी आपने पढ़ा हुआ. अब स्ट्रेस और मॉडुलस ऑफ इलास्टिसिटी का रिलेशन आपने पढ़ा था, स्ट्रेन और मॉडुलस ऑफ इलास्टिसिटी.
Yes, sir.
Same thing is here. Fy or the modulus of elasticity is equal to Fy over epsilon y, I think so. So similarly, epsilon y is equal to Fy over modulus of elasticity. Alright. Now CB is equal to this one plus epsilon s over epsilon s. Yes, I can maybe write this. So this is your CB is equal to 0.003 over E times D over 0.003
Plus Fy.
plus epsilon s.
Fy.
Yes.
So let's say we want to convert it into Fy. We multiply and divide this one by epsilon s. Epsilon s. Alright? We multiply the equation, same.
Sir, Fy, epsilon s and epsilon c, which we studied that.
Epsilon y, sir.
I got it.
Yes.
It's epsilon y.
Fy divided by Fs.
Sorry?
Sir, Fy divided by epsilon s.
It's right, sir. Epsilon y is right, sir. It is also epsilon y, sir.
It's epsilon y to be epsilon y. No, I was just trying to make you clear why this epsilon s come. Actually, my point, I was trying to tell you this one. Why this is at epsilon s? Actually, this here was epsilon y. Epsilon y. No, epsilon y is yield stress of the steel. Epsilon. Go back to the location slide 6, the location neutral axis. We take epsilon s is equal to epsilon y. I think this question also had epsilon s is equal to epsilon y. Right?
Yes.
So this would be equal to epsilon is equal to
Yeah.
Fs over modulus of elasticity. This is clear. This is okay. So my concern is why I
That's not important, sir. They are also divided and multiplied.
exactly. So I want to make this clear just so no one get confused. So from here you find the value of CB. CB is equal to 6. This is in SI unit system, international units. I'm not using foot pound system because there is some also relation in foot pound system that is 7 to 00. This value is 300 is 600. In 600 in place of 600 there is 7 to 00 I think FPS system. Foot pound system. For foot pound system, this 600 replaces with 7 to 00 replaces 600 in FPS system, but I will continue in the MTS system. I will not get in FPS system. Or sometimes if I get in there, so I will check, give you all that details also. So यहाँ से आप find कर सकते हैं the value of depth of the actual stress, actual stress, CB. So again from the same slide, for the balance steel ratio, A is equal to C into beta 1. Now putting the value of CB, we just find the value of CB. You remember? Just find the value of CB. We just put that value here, and we get this kind of relation here. We just replace and put the value of CB here, right? So replace this value. Second, from previous slide again, we find the value of rho B somewhere. You remember this one?
Yes.
We find this value. So rho B is equal to 0.85 beta 1 times FC prime. Here we put the value of AB. AB over D, whatever it is. We just put this value here. Is it clear?
Yes.
We just put here the value of AB. So there are two relations developed here, rho B. So that's not 700, that is 87000. In FPS system, these are two relations that we develop for balanced steel ratio to find out the balanced steel ratio for a given section. How much would be the balanced steel ratio for a specified section if someone gives you that he wants the design of a beam with this much length, this much depth, and this much width. So you have to find, mention the steel that he has to use Fy. So based on all these values, you can find out this balanced steel ratio for that various section. Clear? So that is called design.
सर ये रिलेशन क्या बताता है सर?
ये रिलेशन ये बताता है कि हमें रो बी कैसे फाइंड करना होता है, यानी कि एक सेक्शन जो आपको दिया गया है, आपको एक सेक्शन दिया जाए, ये सेक्शन आपने डिजाइन करना है, इसकी ये डायमेंशन बता दी जाए, ये डायमेंशन आपको बताया जाए, फिर उसको आपको ये बताया कि इसके लिए एफसी प्राइम क्या होगा, हमने ये देखो रेजिस्टेंस कितनी होगी, तो आपने ये करना कि यहाँ पे स्टील में यूज़ करनी है, नीचे
अमाउंट ऑफ स्टील
बैलेंस स्टील रेशियो का ये कहता है, फिर बैलेंस स्टील रेशियो से आगे फर्दर प्रोसेस करते हैं, ये चीज़ बेसिक है। अब कुछ होते हैं ओवर रीइंफोर्स सेक्शन होते हैं, कुछ होते हैं अंडर रीइंफोर्स सेक्शन, एक होता है बैलेंस स्टील रेशियो। हम जो है अभी इसको थोड़ा सा फर्दर डिस्कस करूँगा अभी आगे। नेक्स्ट की स्लाइड, आखिरी हमारी स्लाइड इसी की खत्म हो गई, तो डिस्कस करते हैं।
Sir, we are dealing with balanced.
We are dealing with balanced balance. I tell you why we are dealing with balance, why we not go over under reinforced or over reinforced in the coming slides. There is some sections depending on the flexural behavior. So here you see, one is there are some three control criteria. One is totally compression control, one is totally tension control, and one is between these two. That is transition. So here this comes in compression control criteria. What is for compression control criteria? Make it very, very clear for open book things. There will question be something like that. Someone say, I might say this is compression control criteria. And on the same time, I might say the maximum value of epsilon is 0.002. This is a way. Also, if I use something like this, so I can put a Either I can say it's a compression control criteria. You would guess it's epsilon value is missing. I would say it is finding there. If I say epsilon value is this one, you would be asking, sir, which control criteria? I would say it is. So just make like this. There. Similarly, for the tension control criteria, the epsilon value ranges between 0.002 to 0.005. It ranges in this criteria. The same concept for examination point of view. How would I say use the word? Either tension control criteria, transition control criteria, or I may say the range of this one. And the other third way, I can give the value of 5 factor there. The maximum value of 5.65, or the maximum value of 5 is 0.9, or the minimum value is 0.9, whatever, or it is in between them. So you have to study like this one. So these are the different control sections. That is tension control. In tension control, the epsilon value increases from 0.005. Tension control means that section is no in tension, purely in tension. Compression means its compression is taking everything. But in transition, both are a bit. For this relevant, there is some flexibility. There are some factors here. 5 factors. I think we have discussing in the next slide. What are these 5 factors? Okay, here is one is compression control section here, and you can find this one. This is the actual stress diagram, strain diagram. Sorry, this is the depth of C, or the actual depth of the section, and this one is the D minus C, of course, the remaining one. This is compression control criteria, and for this, the value of concrete is 0.003, and the value of here is less than 0.002. Clear? And if you see the next one, that is tension control criteria, here the concrete value remains the same, but the thing is here, the epsilon T is 0.002 to in the range of 0.002 to 0.005. Clear? And in the third case, is tension control criteria. That's the transition section. Is tension control section. Here the value increases from 0.005.
Sir, compression क्यों same रहता है sir? Compression क्यों same रहता है? 0 point हर section.
We are taking this one as assumption. It's somewhere I have mentioned above there. I think taking I touch it further. So we assuming that the compression is on the same side. Compression is the same value, but tension is and the tension strain is increasing. Strain is same. Strain for all these is constant in the compression area. Compression is not constant.
Yes,
strain is constant over there, but in tension area, strain changes. So based on this, we are defining these 3 sections: transition control section, compression control section, और tension control section.
सर आपने assumption में लिखा था कि अगर जितना स्ट्रेन कंक्रीट में प्रोड्यूस उतना ही ओशन
प्रोड्यूस होगा।
सर यहाँ तो
we are not using that one here. It was for very that part. तुमने बात पढ़ा था, इसका मैं भी आपको आंसर करता हूँ।
Sir, how the string become constant, sir?
String? Just give me a minute. I tell you later on this one. So using similar triangle concept, the previously done, you can find the values of C here in all these cases. All right. Using the same similar triangle concept, you can find the values of here. I tell you later. So this is the strength reduction factor. It's called the 5. The value you see on the vertical axis was the 5. That is strength reduction factor. Now for the tension control section, we take the value of 0.09. All right. You see in the diagram also, previous one is 0.09. It's 0.065. So compression control section. For compression control section, there are lateral ties and spiral reinforcements in columns. You know, in columns, when you go for columns design, there are 2 types of reinforcement. One is called lateral ties, another is called spiral reinforcement. So for those things, those very things we use, that's 0.065 for use for the lateral ties, and for spiral reinforcements we use 0.07.
सर स्पाइरल रेफोर्समेंट जो जॉइंट करते हैं
जी उनको कॉलम्स की जो बार्स होती हैं उनको जॉइंट करने के लिए यूज़ करते हैं टाइज और स्पाइरल रेफोर्समेंट। सो उनमें ये यूज़ करते हैं। जब हम कॉलम पढ़ेंगे इंशाल्लाह हम उसमें ये डिस्कस करेंगे। Then for the transition section, 5 is permitted to be linearly interpolated between 0.65 or 0.7 to 0.9. So अब 0.65 किसके लिए 0.7 किसके लिए होगी. अब इसमें फॉर मेंबर्स विद टाइज, दोज मेंबर्स कॉलम मेंबर्स ऑफ कोर्स जिसमें टाइज यूज़ कर रहे होंगे वहाँ पे हम 0.65 से 0.90 की रेंज में रहेंगे. 5 का फार्मूला ये होगा. और फॉर मेंबर्स जिसमें स्पाइरल हम यूज़ कर रहे होंगे उसके लिए हम वैल्यू एलिवेट कर देंगे 0.75 to 0.90. बाकी फार्मूला ये वही है.
ट्रांजिशन सेक्शन क्या शो करता है सर?
Transition section
Yes, sir.
is not purely controlled by either the lower section, lower part, or the upper part. Both sections are in intermediate stage. None of them has been failed yet.
At neutral axis.
Of course, not at neutral axis. It's not the neutral axis location exactly. It is the section which is controlling the. It is the part. It is the part of the condition which is controlling the whole section behavior. Either it's in tension, whole member, or it's fully in compression, or it is a bit in between. Transition is that stage. Here is the maximum steam ratio. You find the raw balance steam ratio here. Alright, this is the balance steam ratio from the to that slide. For tension controlled section. For tension controlled section, we take epsilon S 0.005 and A I mentioned over there using similar triangle concept. Find the values of C and A. These are the values that you can find from there using similar triangles concept.
Yes.
Okay, so you're putting all these values for tension controlled and for transition control. You can find the row maximum. What would be for this? Okay.
So what's maximum? Sir,
Maximum.
row maximum.
I tell you, is the row balanced? One thing is called over reinforced.
Okay.
Over reinforced, we use maximum value of row. Steel, we use more steel. For under reinforced, we use less steel. So I discuss why we use this one, how we use it in next later slides. For ACA minimum requirement for steel area. Once we find the values of steel, look, you make it sure your values you determine are not less than these. With ACA code requirements is you have to verify everything. If once you find the value of rho B or balance stage ratio, but that must not be less than minimum area stage requirement. This is for SI units and this is for FPS system units. Alright, if you are given in millimeters or something meters, then you can use the SI unit. If it is fruits and inches, you have to use this one. SI units, FPS system. So these are the BW is the width of the section, D is the effective depth, D is FC prime and Fy is the same thing, compressive strength of concrete and the yield stress of steel. Alright. Now here comes the types of failures. One is section is under reinforced or tension failure. Another one is over reinforced or compression failure. And second is the balanced failure. Now try to understand the concept. The word under reinforced or over reinforced in connection with the compression or tension. First thing is under reinforced or tension failure. Now it's under reinforced. Reinforced is less than that required.
Yes.
Yes, sir.
Tension will be more.
Tension will not.
Yes.
Steel takes the tension from green, don't take the tension.
Yes.
When steel is less, so less tension will be accommodated. So failure will be because of tension.
Tension.
Clear?
Yes.
In compression control. So compression control are over reinforced. No, because it's more than the balanced reinforced required. So if more tension is produced, steel can take more tension, but cannot take the compression. No, it's to the concrete. But concrete is on the normal design. If the concrete strength is designed for, let's say, 35 megapascal, if you put the compression load that is equivalent to that is used for the 40 megapascal, 35 megapascal concrete cannot take that. Alright, that is one. So in that case, failure goes to the compression. Failure, the failure type is the compression failure, or you can term it as a over reinforced. Or in the same case, if your the value is the same, but your tension produced, but your steel is working very well, they are over reinforced. You put the more reinforcement than the usual required, so there will be no failure because of tension. That will be because of compression. Yes.
सर ये दूसरा समझाना सर, ज़्यादा स्टील प्रोवाइड करते हैं तो कंप्रेशन एरिया में क्रैक्स कहाँ से प्रोड्यूस होते हैं, कैसे प्रोड्यूस?
जब आप स्टील ज़्यादा प्रोड्यूस करते हैं, नो, फर्स्ट थिंग टेक द keep it in mind, concrete and steel, and also steel is more than the usual requirement, more than the normal requirement. You put some loading and whatever the moments, you have heavy amount of produce tension over there. Steel will not crack, steel will not fail. You put more steel over there. You have put more steel. It's over reinforced. It can tolerate, it can accommodate more tension. But your concrete cannot have so much efficiency that it can tolerate so much loads.
सर टेंशन तो प्रोड्यूस ही नहीं होगा जब स्टील का ज़्यादा प्रोवाइड।
This is not only tension. This is not the concept of only tension. Loading does not only produce tension. There is always compression and tension. If you see the layer one, case one for example, neutral axis is fixed, but tension and compression forces may increase with load. Got my point?
Yes.
Neutral axis remains fixed in the first case, but the tension and compression forces increase. If you see the second case, neutral axis goes above as tension and compression forces increase. If the forces increase, cracks appears. The depth of neutral axis move up. You got my point?
Yes.
Neutral axis moves up. फोर्सेस इंक्रीज होने से क्या होता है, अब चूंकि वो क्रैक्स हो रहे हैं, उसमें क्रैक्स डेवलप हो रहे हैं, अब कंक्रीट में क्रैक हो रहा है, कंक्रीट फेल हो रहा है, स्टील नहीं हो रहा, कंक्रीट फेल हो रहा है, कीप इट इन माइंड, कंक्रीट फेल हो रहा है, स्टील नहीं, cracks will move up. Third section is varies for each failure type accordingly. That's a balanced failure. So that depends upon the loading conditions. वो vary करेगा loading condition के ऊपर, वो किस तरीके से failure हो रहा है. So it's balanced. वो जो भी load होगा वो आपको उस पर fail होगा. Accordingly the tension उसमें ज़्यादा develop हो जाती है किसी तरीके से, तो वो स्टील है वो उसको tolerate नहीं कर सकेगा. Compression उसमें ज़्यादा develop हो गई है. तो उसको complete.
सर तीनों के लिए लोडिंग कंडीशन सेम होगा?
नहीं, चेंज हो रही है ना.
तो सर ये तो एक ही सेक्शन है, आप
एक ही सेक्शन में आप ओके मैं यही एक सेक्शन है, इसी तरीके के 3 सेक्शन क्रॉस कर रहे हैं, एक को बैलेंस करते हैं, एक को ओवर रीइंफोर्स कर दें, एक को अंडर रीइंफोर्स कर दें, लोडिंग कंडीशंस कर दें, दे विल बिहेव डिफरेंटली,
डिफरेंट लोडिंग कंडीशन.
अगर आप सेम लोड कंडीशन रखोगे, लेट्स से उसमें बैलेंस वाला फेल हो जाएगा, लेट्स से एक लोड कंडीशन इसमें बैलेंस वाला फेल हो जाता है, जो अंडर रीइंफोर्स वाला वो भी फेल हो चुका होगा. अंडर रीइंफोर्स इज लेस देन द बैलेंस रीइंफोर्समेंट, बट ओवर रीइंफोर्स विल बी स्टिल. ओवर रीइंफोर्स विल क्रैक एट द एंड इन केस ऑफ टेंशन. अगर उनकी कंप्रेशन कैपेसिटी सबकी सेम है, कंप्रेशन स्ट्रेंथ जो उनमें डेवलप हो रही है, अब कंप्रेशन स्ट्रेस कैसे डेवलप होती है? कीप इट इन माइंड दैट डेप्थ ऑफ द अनक्रैक्ड सेक्शन, कंप्रेशन फोर्स डेवलप होगी वो अनक्रैक्ड कंक्रीट की वजह से. ये केस की बात करें कि न्यूट्रल एक्सिस गोज अप, न्यूट्रल एक्सिस जैसे ही ऊपर जाता है, एज इट गोज अप द सेक्शन डेप्थ रिड्यूसेस अनक्रैक्ड. जब अनक्रैक्ड डेप्थ रिड्यूस होगी तो उसका एरिया रिड्यूस हो जाएगा, सो कंप्रेशन फोर्स रिड्यूस हो जाएगी, कंप्रेशन स्ट्रेंथ जो उसकी रेजिस्टेंस है या दूसरे वर्ड में जो रेजिस्टिंग मोमेंट होता है वो रिड्यूस हो जाएगा. फॉर अंडर रेनफोर्स्ड लास्ट स्लाइड आ भी गई है. For under reinforced tension failure, this is a fun formula. There's derivations. There was derivation, I didn't put the derivation. I just put the direct formulas. So don't ask, ये कहाँ से आ गया, वो कहाँ से आ गया. I just put the derivation, क्योंकि derivation में पेपर में दे दी नहीं है, इसलिए मैं ट्राई नहीं करा नहीं है. इनके लिए derivation मैंने डाली. ये फार्मूला आपको याद करना पड़ेगा, आपके पास पड़ा होगा, ओपन बुक है. ठीक है जी, यहाँ पे ये आपके पास वही फार्मूला. सिंपली अब रो की वैल्यू ये रिलेट किया गया इन टर्म्स ऑफ ओमेगा इंटू 1 माइनस दिस वन, ओमेगा की वैल्यू क्या है वो भी मेंशन है और आर की वैल्यू क्या है वो भी मेंशन है। आई रिपीट, ये फार्मूलाज डिराइव्ड अगर किसी को डेरिवेशन चाहिए तो वो मैं दे दूँगा, बट इट्स नॉट लाइक कोर्स और सिलेबस, तो मैंने उसको नहीं डाला। सो डोंट गेट कंफ्यूज कि ये कहाँ से आ गया वो कहाँ से ला आ गई, जो कुछ रेलेवेंट था वो मैंने कोशिश की तो वो मैं डाल दूँ। अब इसमें अब जो रो की वैल्यू है उसको इन टर्म्स में लिया गया। अब रो में ओमेगा किसके बराबर है 0.85 टाइम एफ सी प्राइम ओवर एफ वाई, और आर जो है एम एन जो है नॉमिनल मोमेंट और बी डी स्क्वायर। ठीक है, अब जो डी मिनिमम फाइंड करनी है, एक्चुअली बेसिकली मकसद ये है कि डी मिनिमम कैसे फाइंड करना है, ये डी जो है। अब डी मिनिमम फाइंड करने के लिए आपके पास इन्हीं से आगे फर्दर जब प्रोसेस करते हैं आप डी मिनिमम आपके पास ये फार्मूला अल्टीमेट आपने फार्मूला ये यूज़ करना है, बाकी नहीं। डी मिनिमम का फार्मूला यूज़ करना है, ये डी मिनिमम है। इफ़ डी इज़ ग्रेटर देन डी मिनिमम द सेक्शन विल बी अंडर रीइंफोर्स्ड। इफ़ डी आप जो डेप्थ फाइंड करते हैं, आप सेक्शन की डेप्थ फाइंड करते हैं, अब एनालिसिस कर रहे हैं, पहले डिफाइन कर लिया आपने, अब उसको एनालिसिस करने जा रहे हैं। जब आप उसकी डेप्थ फाइंड करते हैं, क्या ये डेप्थ जो एक पहले बेस विड्थ और डेप्थ की बेस पर आपने स्टील फाइंड किया, अब उसको रिवर्स करते हैं, एनालिसिस करने जा रहे हैं, आप फाइंड करते हैं दूसरे में से डेप्थ मिनिमम डी मिनिमम फाइंड करते हैं, इसकी मिनिमम डेप्थ क्या है। अब मिनिमम डेप्थ जो हुआ है वो इस लिमिट तक रहनी चाहिए, जो फार्मूला गिवन है द मिनिमम डेप्थ शुड बी एट दिस, यू हैव फाइंड यूजिंग दिस फार्मूला, बट द डेप्थ यू कैलकुलेट फॉर योर सेक्शन, if that is less or more whatever in relevant, if it is less than the day minimum then it is under reinforced section. Let's say in paper point of view, so I will not ask you whether in specific this one, okay, अब इसमें क्या होगा, अब ये कहा जाएगा प्रूव करें कि अंडर रीइंफोर्स है या ओवर रीइंफोर्स है। सेक्शन ये है whether the section is under reinforced or over reinforced। अब आपको साइंस में करना क्या है
सर, डिफाइन करें
कंडीशन, ठीक होगी बात।
सो एक क्लू ये है कि जो
बस जो है वो पेपर में करना, पेपर में पूछना है ना बस। ओवर रीइंफोर्सिंग कंप्रेशन फेलियर, आई रिपीट अगेन कि मेरे ख्याल से कुछ लोगों को शिकवा होगा, इस जो है ना कंफ्यूजन होगी फार्मूलाज की। वो डेरिवेशन पढ़ी, वो डेरिवेशन में से ले सकते हैं, बट आई डिडंट ऐड क्योंकि मैंने वो पेपर में देरी नहीं, तो मैं क्यों उसको ऐड करूँ। अब ओवर रीइंफोर्सिंग कंप्रेशन फेलियर, अब यहाँ पे चीज़ नोट करें, सडन फेलियर विद नो वार्निंग। अब कंप्रेशन फेलियर क्या होती है, कंप्रेशन इज कंक्रीट फेल होता है, वो तो यील्ड कर रही है अभी, वो तो भी यील्डिंग स्टार्ट करती है ना स्टील। अब इसमें क्या है, कंक्रीट टचेस गिरना शुरू हो जाते हैं, दैट इज सडन फेलियर। बस आप देखें you can find so many cases, earthquake आता है whatever, स्टील नहीं टूटता, कंक्रीट निकल जाता है, दैट इज सडन फेलियर, वार्निंग नहीं। अब यूज फॉर एनालिसिस ऑफ एक्सीडेंटल ओवर रीइंफोर्स्ड सेक्शन, अब ये चीज है ओवर रीइंफोर्स्ड कंप्रेशन फेलियर जो है, इस यूज पर जस्ट एनालिसिस डिजाइन नहीं किया जाता, ओवर रीइंफोर्स्ड सेक्शन डिजाइन नहीं किए जाते, ओवर रीइंफोर्स्ड सेक्शन डिजाइन नहीं किए जाते। अब ये सारा मेथड सिर्फ यूज की जगह चेक करने के लिए क्या जो मेथड या क्या जो सेक्शन डिजाइन हुआ है वो ओवर रीइंफोर्स्ड तो नहीं है, जस्ट टू चेक दिस, डिजाइन नहीं किया जाता सेक्शन, उसको एनालाइज किया जाता है क्या जो सेक्शन डिजाइन किया है वो कहीं ओवर रीइंफोर्स्ड तो नहीं हो गया। इट्स नॉट परमिटेड बाय एसीए फॉर डिजाइन। सो नॉमिनल मोमेंट क्या होता है उसकी ये वैल्यू साफ लिखी हुई। अब जो आखिरी सेक्शन है बैलेंस फेलियर, उसके लिए टेंशन फार्मूला, टेंशन जोन के लिए और कंप्रेशन उसके फेलियर के लिए जो है ये उसके फार्मूलाज, दो फार्मूलाज गिवन है।
सर डिज़ाइन सिर्फ अंडर रीइंफोर्समेंट करते हैं बस,
डिज़ाइन जो है वो बैलेंस ठीक है, इसमें मेरे से आगे कुछ और ऐड किया ख़त्म हो गया, एक था मैंने शायद वो ऐड नहीं किया कि उसमें जो है सेक्शन जो है वो डिज़ाइन करते हैं फॉर